So far, we've talked about performing hypothesis tests where we're taking a look at our population parameter and trying to make some conclusions about it based on having a single sample of data. But sometimes we have things instead where we have two samples that we're really looking to compare in some way, shape, or form. Say something with a control group and an experimental group. So this is where we're going to get into two sample hypothesis tests and then eventually something even more than just two samples. So when we look at having a control and experimental group, we're really asking a few key questions. So one key question, are the differences between those groups just due to chance, or do they reflect some real association? So when we look at these, we should have some sort of difference between what the results are. The smaller the difference, between the groups, the more likely the difference is just chance. All right, so there are a couple of different things that we might look at when we're looking at comparing and performing a hypothesis test for multiple samples. One thing we might do is the difference between two means, where we have samples that are independent of each other. So a question that might be related to this would be, do computers help high school students learn math? One way to address this would be to give a test in two sample students, one with a group of students who used computers in their math classes and another from a group who didn't use computers. If the difference between the sample mean test scores is large enough, then we could conclude that there actually is a difference between those populations. So our data here is two independent samples. We want to know how strong the evidence is that those population mean scores are different. So let's talk about some notation for this problem. When we're talking about mu1 and mu2, these are going to be our population means. So we have two different populations, each one of them is going to have their own mean, and we're also going to have from each of these samples their own sample means, x bar 1 and x bar 2. So the subscript is going to help us kind of split up these different populations that we have. These are our sample means. And then everything else is going to be kind of denoted in a way you'd expect. Little s1 and little s2 will be the sample standard deviations, and little n1 and little n2 are going to be the respective sample sizes. All right, so when we go to create a null and alternative hypothesis for this sort of test, what we'll do is our alternative, so I'll write the alternative for each of them. Remember, the null hypothesis is just the complement. We could have one of three different outcomes we could be looking at. We could be looking at mu1 minus mu2 is greater than mu naught. I'll talk about what mu naught is in a second. It could be mu1 minus mu2 is less than mu naught, or the alternative could be mu1 minus mu2 is not equal to mu naught. So mu naught is going to be the size of the difference, and this is going to come from the null hypothesis H naught. It's usually going to be 0. So usually we'll be saying, can we say that one is better than the other or not better? And usually when we're doing this, we're not specifying a magnitude by how much better or greater than or less than something is. And so when we're not specifying that magnitude, usually we're going to see 0. Now, last but not least, we have our test statistic itself. So here, because we're dealing with sample standard deviations, we're going to have to use the student's t-distribution again. So when I write the squiggly t, the approximately t later, we'll talk about how many degrees of freedom we have. So to calculate this, we'll take x bar 1 minus x bar 2 minus mu 1 minus mu 2, which, if you'll notice, we're going to end up having this part be equal to whatever mu naught is from our null and alternative hypothesis. And this gets divided by the square root of the standard deviation for the first sample squared over its sample size plus standard deviation of the second sample squared over its sample size. And this is approximately going to be approximated by our t-distribution with a certain number of degrees of freedom. So this degrees of freedom is going to be equal to the smaller of n1 minus 1 and n2 minus 1. So whichever is the smaller of those is going to be our sample size. Normally for a t-distribution, we're looking at the sample size minus 1, and so we're going to pick the smallest of those to be our degrees of freedom. Now, there are some assumptions that we're making when we're conducting this test. So one assumption is that we have a simple random samples from two populations. Another is that the samples are independent of one another. And the last is that each sample size is large. In this context, it means each of the n sub i's are greater than 30, or the population is approximately normal. So what we didn't do there is we didn't actually do an example of how you would go ahead and then do the calculation for that. So I'll get through a couple of examples at the beginning of for the beginning of the worksheet with this at the end of the video. But recognize that for hypothesis testing, what we're doing is we're calculating a test statistic, and then we'll either go ahead and calculate a critical value to compare that test statistic to, or use the test statistic and whether or not it's left tail or right tail, we use that for critical value as well, to find a p-value. So the only thing that really is changing from when we did one sample is how we calculate this test statistic. So for two means that come from independent samples, this is how we're going to calculate that test statistic. So if I were, say, a student taking this class, what I would do is I would go ahead and maybe kind of create a little list for myself on the side, especially when I'm trying to take the exam, so I can kind of brush up on, oh, okay, that's how we calculate that test statistic based on that information. Okay, now, note that we immediately assumed that the sample standard deviations are the things we had to work with. It is possible that we have the population standard deviations for both of our samples, but that's rarely known. If you did have it, however, you're calculating the test statistic almost identically. So numerator does not change. The only thing about the denominator that changes is that now we're going to be substituting in those population standard deviations. And what this does to us is it actually makes it so that we're now using z-scores instead. So remember that if you don't know the population standard deviations for these, you'll be using the student's t-distribution, and honestly that's what you should expect most of the time in the real world, but there are some kind of corner cases where you could use z-scores instead. So remember, z-scores mean you know the population standard deviation. Student's t-distribution means you don't know it. That was the thing I think I saw a couple of people mess up on the test, so I wanted to mention it. All right. We also could talk about the difference between two proportions. So here a question that might be asked is something along the lines of, are older, more experienced workers more likely to use computer at work than younger workers? To answer this question, we could take a sample of employed people ages 25 to 40 and ask if they use computer at work, and separately ask people 41 to 65 if they use computer at work. And then what this does is this gives us a proportion for each of our two samples. So again, we have two independent samples. And here our notation is going to be P1 and P2 will be our population proportions, and P1 hat and P2 hat are going to be our sample proportions. So our null and alternative hypotheses, here I'm going to talk about the alternative hypotheses. Remember, null is just the complement of it. So similar to before, we're going to have P1 minus P2, similar to how we had mu1 minus mu2, could be greater than 0. We could also rewrite this to be just P1 is greater than P2. And kind of following along that format, we could have a different alternative hypothesis, say P1 is less than P2, and we also could have a possible alternative hypothesis of P1 is not equal to P2. So remember, these are all different possibilities for what the alternative is. It's not going to be all of these at once. And if you want to find the null hypothesis, it is the complement of these. So for our test statistic, normally if we were looking at the mean for the proportion, the sample proportions, it would be the population proportion. And if we were looking at the standard deviation for those proportions, we would be looking at the square root of p times 1 minus p over n. Now here, what we're going to assume, our assumption is that P1 equals P2, and so our standard deviation, when we're looking at these, is going to end up becoming P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. If you take probability theory, I believe you get a little bit into how this ends up coming up. And what we want to do is we'll go ahead and we're going to assume, if we're using this standard deviation, that we know P1 and P2. However, we don't often have P1 and P2. We don't know knowledge about the overall population. We just know what our information is for our samples. So instead, if we knew P1 and P2, this is our standard deviation. But since we don't know that, instead, we can use a pooled proportion. And we'll call it p hat, and this will be x1 plus x2 over n1 plus n2. So remember that when we're coming up with our sample proportions, these x1s and x2s are the number of successes, the number of people in that category, divided by the total number of people sampled. So in other words, we're going to treat the two samples as one big sample. We go to make this calculation, and our test statistic is going to be p1 hat minus p2 hat minus p1 minus p2, which this will equal 0 from h naught. So here we talked about how this will be 0, so that'll be our assumption that we're using for our null, and this will be over square root of p hat times 1 minus p hat times 1 over n1 plus 1 over n2. And so remember, this p hat is going to be this proportion, and we're running out of room. This whole thing is going to be approximated by a z-score. Box this off. So what we're doing here is we'll calculate this test statistic using the formula. So we'll be taking basically the difference in our proportions and dividing by this square root using the pooled proportion in order to figure out the test statistic. And we're going to be using the z-scores, so inverse norm, normal CDF, that sort of thing. Now, when we do this sort of test, there are some assumptions we're making. So a lot of these assumptions probably won't be surprising. There are two simple random samples that are independent of one another that we're using. Each population is at least 20 times as large as the sample drawn from it, so we're using a small enough group of the population that we're drawing from something that we can kind of make our assumptions about independence. Both individuals in each, or the individuals in each sample are divided into two categories, and both samples contain at least 10 individuals in each category. So in other words, if we went back to talking about this example of people who were likely to use a computer at work, what we're saying is people in the 25 to 40 group, we'd have at least 10 people who did feel they were more likely to use a computer at work, and at least 10 people who felt they were less likely to use a computer at work. And then same for the age 41 to 65 people, there'd be at least 10 people who felt they were more likely to use the computer at work, and at least 10 people who felt they were less likely to use the computer at work. And so we're assuming that you can either be more likely or less likely. We're assuming, since we're saying we're divided into two categories, that there can't be a, no, I use them about the same. All right, you have to pick one in this case. All right, so our last type of two-sample hypothesis we might have is for paired samples. So we want to know, does tuning a car engine improve the gas mileage? So suppose we sampled 8 automobiles to determine their gas mileage before a tune-up and then again after the tune-up. The samples are then paired because every value is from the before tune-up is paired with the same car after the tune-up. So some notation for us, we're going to have d bar. This is going to be the sample mean of the differences between the values in the matched pairs. Here, S sub D is going to be the sample standard deviation of the differences. And mu D is going to be the population mean difference for the matched pairs. So here, our alternative hypotheses that we have are going to be about taking this mean difference and comparing it to whatever mu naught is. So mu naught should be given, whether it's a difference of at least 10 or a difference of 5 or difference of however many. We also say that the mean of our differences for the population should be less than some value or not equal to some value for our alternative hypotheses. So remember, null hypotheses are just going to be the complement of these. So here we have the mean of the differences greater than the sum number, then the null hypothesis is that it's less than or equal to, and so this would be greater than or equal to for the null, and this would be equals to for the null. Our test statistic here is going to take d bar minus this mu naught that we have divided by our sample standard deviation from our differences over the square root of n. And this is going to be approximated by, again, a student's t-distribution, because again, we're looking at just all this sample information. So we want to talk about how we can compare paired data versus this idea of having two means that we were looking at before. When we have this paired data, we have something much more streamlined because we're only looking at a single standard deviation instead of two, and we're looking at a single sample size instead of two. Here again, we're taking our difference in our averages. This is the average difference, and we've got some sort of mu naught we're subtracting. But in either case, we're taking our t, and again, the degrees of freedom here is n minus 1. Much less difficult to calculate than when we're looking at two independent samples. So some assumptions that we have here is that we have a simple sample of matched pairs, and we also assume that either the sample size is large, greater than 30, or the differences between the matched pairs are approximately normal. Which means that our d bar, our sample means for our differences, are going to be approximately normal. I'm no longer on the page. That sudden realization when you're no longer on the page. Okay, so we've got these different test statistics. And so what worksheet 9 is going to have you do is it's going to have you go through some examples of trying these out and trying to get a sense of how to use these. And again, like I had mentioned kind of in the middle of the video, when we're looking at all of these, the main difference between what we have now and what we had before is that the way we calculate our test statistic and the way we talk about our null and alternative are different. But these ideas of p-values and critical values don't change. So let's go through the first two examples so you can kind of start to see, based on both the p-value method and the critical value method, what I mean by this. So, the first example says the National Assessment of Educational Progress tested a sample of 60 students who used a computer in their math class and another sample of 40 students who had not used a computer. The sample mean score for the students using a computer was 309 with a sample standard deviation of 29. So this is that example we had talked about at the very beginning. For students not using a computer, the sample mean was 303 with a sample standard deviation of 32. We want to conclude at the 0.05 significance level, the mean scores differ. And so we want to do this using the p-value method. So first we need to find our null and our alternative hypotheses. So we want to know if the mean scores differ. So the alternative is that they are not the same. And the null is that they are the same. So since we don't have any difference here, we could convert this into what we saw before, mu1 minus mu2 equals 0. And so here that mean difference is going to be 0. So when we're calculating our test statistic, we're just going to take x1 bar minus x2 bar minus 0 because there's no proposed difference between them. And we're going to divide by their standard deviation for the first sample squared over the first sample size plus the standard deviation squared for the second sample over the sample size for the second sample. And so this is going to be 309. So we had 309 from the first, an average of 303 from the second, and we'll divide by the square root of the first standard deviation was 29, and there were 60 students, so 29 squared over 60 plus 32 squared over 40, so 32 was that sample size from the second sample, 40 was the that was the standard deviation for the second sample, 40 was the sample size for that sample, and provided that I did my calculations correctly last year when I did this, we got 0.953. Be very careful here with all the parentheses, and this is going to be approximated by the student's t-distribution, so we need to know what we have here. So since we're not using not equals to, this symbol, remember, tells us that we have a two-tail test. And so when we take a look, here we've got our 0. Then over here, if we're looking at two-tail, we've got 0.953 this side that we need to calculate the area under the curve for, but since it's not equal, negative 0.953 exists on the other side that we have to calculate the area to the left of as well. So when we're looking to find this p-value, because we're using the student's t-distribution, we're using TCDF, we want to go from 0.953 to infinity, and our degrees of freedom is the minimum of 60 minus 1 and 40 minus 1, because those are our sample sizes, and so it's going to be 39. But then we need to multiply that by 2 because we have this area, and it's going to be the same as this area over on the other side. So this is going to be approximately 0.346, which is definitely greater than 0.005. So what does this mean? It means we're going to fail to reject. So based on this information, we fail to reject the null hypothesis. So in other words, what we're saying is this does not give us enough information to tell us that there's a noticeable difference between the students that were using a computer in class versus the students who were not using a computer. Alright, so that was using the p-value method. Again, the only difference between this and one sample is what we called our null and alternative hypotheses, and then how we phrased this idea of getting this test statistic. This p-value calculation didn't change. All right, so looking at another example. Treatment of wastewater is important to reduce the concentration of undesirable pollutants. One such substance is benzene, which is used as an industrial solvent. Two methods of water treatment are being compared. Treatment 1 is applied to 5 specimens of wastewater, and treatment 2 is applied to 7 specimens. The benzene concentrations in milligrams per liter for each specimen are as follows. So we get these as our different values. We want to conclude we want to know if we can conclude the mean concentration for treatment 1 is more than 1 milligram per liter greater than the mean concentration of treatment 2. Now what we're going to do is we're going to assume that these are coming from things that are normal enough so that we don't have to worry about the fact that these are such small sample sizes. So if you are still having trouble with concept 1, I want you to take a moment and try to calculate the mean and standard deviation for both of these. In the meantime, I want to go ahead and kind of give us most of the other information. H naught here, the null hypothesis, is going to be that mu1 minus mu2. So we said we want to conclude that the mean concentration for treatment 1 is more than 1 milligram. So more than is not including that, so that's going to be our alternative. So mu1 minus mu2 is the alternative, and so mu1 minus mu2 is less than or equal to 1 is the null hypothesis. Alright, so if you're still calculating these, or you just want to double check your work, for these samples, x1 bar is going to be 6.84, x2 bar is going to be 5.7, S1 is going to be 0.8989, S2 is going to be 1.571, and then we also know that N1 is 5 and N2 is 7. So then when we go to calculate our statistic, we're going to have our x bar 1, so 6.84. So it's going to be the same formula as before, except now, because we have something that is not just 0 for mu naught, we have 1, we'll have to subtract that as well. So 6.84 minus 5.7 minus 1 over the square root of 0.8989 squared over 5 plus 1.571 squared over 7. And so we should get approximately 0.1952, which is going to be approximated by our t distribution with degrees of freedom equal to the minimum value between 5 minus 1 and 7 minus 1. So here it'll be 4 degrees of freedom. And let's take a look at what we have here. We have 0 as maybe proposed, where we'd expect the distribution to start. So that might not be 1952. Actually, that would still be the mean. I don't know why I second guessed myself for a second there. So there's our value, there's 0. We want to use the critical value, and because we're looking at being greater than 1, we're going to have a right tail test. So in order to do that, we need to figure out what value of t, if we're looking at a significance level of 0.05, it'll have 95% of the area to the left of it. So we'll have inverse t of 1 minus 0.05, and we have 4 degrees of freedom, and we should get approximately 2.132. So if we have 2.132, that's going to be over here. And being a right tail test, we're shading to the right. And so what we can see here is that our value for our test statistic wasn't past or more extreme than the critical value. And because of that, so since 0.1952 is less than 2.132, we fail to reject H naught. Alright, so I'm hoping that kind of going through these first two helps illustrate some of the main differences between one sample and what we now have with two samples. If you're looking at this and it is the week that two sample hypothesis test, if this is the week that this video came out and you haven't seen goodness of fit yet, you can still get through most of the questions, right? So we've got 2 more questions on the next page, 2 on the page after that, where we get into kind of some paired things. Here we even found if you have questions while you're working on these, let me know.